Yes, ma'am.
Yes, ma'am.
Yes. So we were talking about the canonical cover, and what we stated, suppose we are having a set of functional dependencies F, then whenever user performs an update on a relation in database schema, the database system must ensure that every functional dependency in F is satisfied. So if it happens that any of the functional dependencies in F is violated, then system needs to roll back that particular update, right? So for every update now, the system is having this additional task. In fact, this set of functional dependencies comprises of the constraints in the form of functional dependency, and we need to satisfy all those constraints while updating our database. Now, to reduce the task of checking each and every functional dependency in F, what we can do is we can come up with a simplified set denoted as FC, right? Such that the closure of F, that is F plus, and closure of this new set, simplified set FC plus, both are same, right? So instead of checking each functional dependency in set F, what we can do is we can check every functional dependency in simplified set FC, right, for its violation. And if we try to check the functional dependencies from this simplified set FC, it would be more easier, and the efforts those are required are less than checking the functional dependencies in F. And this is what the concept of canonical cover, right? So sets of functional dependencies may have the redundant dependencies that can be inferred from the other dependencies in the set. Say for example, in the original set of functional dependencies F, we have been provided with these three dependencies: A determining B, B determining C, and A determining C. But as we know, if A determines B and B determines C, actually by transitivity, it is possible for us to come up with this A determining C. So, while checking the functional dependencies for its violation, in fact, checking A to B and B to C is enough. If these two functional dependencies are satisfied, obviously A to C must be satisfied, right? So we may say that this functional dependency A to C is redundant in this set. Do you agree with me? Yes?
Yes, ma'am.
Fine.
Yes, ma'am.
Fine. So, if this functional dependency is redundant, it is not mandatory now for us to have this dependency in set F. So, we can omit such kind of redundant dependency. Even we may have part of functional dependency that can also be redundant. Part of functional dependency that can also be redundant. What we mean by this? Let us assume that we are having now this set of functional dependencies A to B, B to C, and A to CD. Right? So, if we look at this functional dependency, to the right hand side of the dependency, we are having two attributes. Right? So, we may check whether any of the attributes in this right hand side is actually extra. Even if we omit this attribute C, there will not be any harm. So even if we omit this attribute C from the functional dependency, it is possible for us to come up with this dependency A determining CD by making use of this simplified set of functional dependencies. So this A to B, B to C, A to CD can be simplified to A to B, B to C and A to D by removing the extraneous attribute C. So we talked about the extraneous attribute in the right hand side of the dependency. But we may have the extraneous attribute in left hand side as well. Say for example, if we are having the dependencies like A to B, B to C and AC to D, this can be simplified as A to B, B to C and A to D. So here we may observe that this left hand side of the functional dependency AC to D is having this attribute C, which is extra. So it is possible to omit this attribute, and even though we omit this attribute and we come up with this simplified set of functional dependencies, by making use of these dependencies, it is possible for us to infer this AC to D, right? And that is why it is not necessary actually to have this attribute in the functional dependency, right? So we are going into the details. So a canonical cover of set of functional dependencies F is a minimal set of functional dependencies equivalent to F, having no redundant dependencies or of dependencies. So if my original set is F and the simplified set is C, right, such that the closures of both these sets are same, right? So let's proceed now with the concept of extraneous attribute. So consider a set F of functional dependencies, and the functional dependency alpha to beta exists in F. So we are having set of functional dependencies F, and we are having one dependency like alpha determining beta. Now, attribute A is extraneous in alpha, that is the left hand side of the functional dependency. Attribute A is extraneous in alpha if A belongs to alpha and F logically implies this new set of functional dependencies. So what this set is, F minus alpha to beta union alpha minus A to beta. So what does this mean? See, attribute A is extraneous in alpha. Alpha is my left hand side of functional dependency. So attribute A is extraneous in left hand side of the functional dependency if that attribute A belongs to the left hand side of dependency. A belongs to alpha, and F logically implies the new set F minus alpha to beta union alpha minus A to beta. What does this mean? See, what we are trying to do is we are trying to come up with a new set of functional dependencies by simply omitting the attribute under consideration. So, given set F with a functional dependency, say alpha to beta, right? This alpha contains one attribute as A. We are saying that this attribute A is extraneous if this A belongs to the left hand side of the functional dependency, that is A belongs to alpha, and this F logically implies the new set F dash. Let us assume. So we are going to find see F minus alpha to beta. What does this mean? In this new set, we are not going to have this alpha to beta. We are going to omit this alpha to beta from original set F. Right? So whatever remains, meaning if I am having few more functional dependencies in this set, then all those dependencies will be there, except this dependency alpha determining beta. Right? Union. So we'll be having all remaining dependencies. Union alpha minus A to beta. What does this mean? We are adding now dependency such that we will be having now the new dependency that we may get after omitting this attribute A from left hand side of the functional dependency. So what we will have here is, we will not have this alpha to beta as it is. Instead, we will be having all remaining dependencies plus we will be having alpha minus A to beta. That means we are going to omit this attribute A from left hand side, and then whatever may be my left hand side, that is alpha minus A determining beta, would be there in my new set of functional dependencies, alpha minus A to and all remaining dependencies. So this would be my new set F, right? Sorry, new set F dash. And if my original set F logically implies this new set F dash, if this original set F logically implies this new set F dash, then we declare that this attribute A is extra in my left hand side of the function dependency. Right? We are going to look at one example so that the idea gets clear. Similarly, we may find whether the attribute A is extra in the right hand side of the dependency. So, attribute A is extraneous in beta. Beta is my right hand side of the functional dependency. So, attribute A is extraneous in beta if A belongs to the right hand side and the set of functional dependencies, this new set, logically implies the original set F. So how we are going to come up with this new set F dash? On the similar lines, this new set is being computed as F minus alpha determining beta union alpha determines beta minus A. So simply by omitting this attribute A from the concerned dependent, whatever we get is our new set. So we are saying that A is extraneous in right hand side of the functional dependency if the new set F dash logically implies my original set F. right? So let us see the example. Given the set of functional dependencies F having two dependencies A to C and AB to C, right? So we may say that this B is extra. This B is extra in this functional dependency AB to C. So this is my left hand side of the dependency, right? Now we are checking whether this B is extra in this dependency AB to C. So when we are going to say that this B is extra in left hand side of the functional dependency, if this F logically implies new set F dash. So what I will have in new set F dash? I will have in this new set F dash F minus alpha up to beta. So I am omitting this, and whatever are remaining functional dependencies, those will be present in my set F dash. What else I will have? Union alpha minus A to beta. So this is my alpha and this is my beta. This functional dependency is under consideration. So simply what I am going to do is I am testing for this B. So simply I will be omitting this B from my functional dependency, and whatever remains, meaning I will be having now, after omitting this B from this dependency, I'll be having A to C, right? Once again. So I'll be having this A to C after omitting this B from my left hand side, because I'm testing for this B. Right? Implies this new set F dash, then I will say that this B is extraneous and I can omit that, right? So whether this F implies my F dash, whether this F original set implies this new set F dash. Yes. Original set is A to C, AB to C. New set after omitting this B, because I am testing for this B whether it is extra, right? So omitting this attribute B from the functional dependency, I come up with once again A to C, right? So ultimately my F dash new set is A to C, having only dependency A to C, right? So simply I am testing whether this original set F implies this F dash, meaning whether by making use of these functional dependencies, whether it is possible for me to imply this dependency A to C. Obviously yes. Why? Because A to C already present in my functional dependencies, set of functional dependencies. So A to C is already there, and that is why I may say that B is extraneous in AB to C, because A to C and AB to C, that means the original set F logically implies new set F dash, wherein I am having the only dependency, that is A to C, right? So if this is the case, then I'll say that B is extra. Similarly, I may have another example. If this is the set of dependencies, then I am testing now the attribute, extra attribute in RHS. So here I may say that this C is extra. I may say that this C is extra in AB to CD. Why? Because new set F dash. So how I am going to form this new set F dash? This new set F dash is A to C and AB to D. This is my new set. Why? Because I am testing for this C. So simply what I am going to do is I am going to omit this attribute C from RHS now. And whatever remains will become my F dash, new set. And now I am checking whether this F dash determines F. Whether this F dash logically implies F. So, whether A to C and AB to D logically implies this original set F, when I am having A to C and AB to CD. Meaning, I need to check now whether this F dash determines AB to CD. Getting me? Whether this F dash determines the functional dependency AB to CD. The origin. So please tell me now whether AB to CD can be inferred by this F dash. Use Armstrong's axioms, those we have seen earlier. Yes. Can we infer AB to CD from these two dependencies in our F dash? Yes? By making use of these two, can we come up with this dependency AB to CD? Use Armstrong's axioms and check it out. Yes? How we can do that? It is very simple. Why you people are not responding, I don't know. See, what I can do is, I can augment B here in this functional dependency. So I come up with AB to BC. Right? Now, I am having this AB to BC and I am having this AB to D. So, left hand side is same. So, I may use union rule here and I may come up with AB to BCD. Correct? AB to BCD. Meaning, AB determines B, and if I use now decomposition rule, AB determines B, right? AB determines C and AB determines D. So obviously AB determines this CD. AB determines this CD, and that is what we wanted to check. Right? So even though we omit this functional C from this functional dependency AB to CD, the new set of functional dependencies A to C, AB to D can infer the original functional dependency AB to CD. So there is no harm in omitting this attribute C from this functional dependency AB to CD. Right? So we say that in this case C is extraneous in the RHS of the dependency AB to CD, and it is possible for us to omit this C because it is extra. It is not making any difference. So we are simplifying this set. A to C, AB to CD can be simplified as A to C, AB to D. Are you getting me? Yes?
Yes, ma'am.
Please understand the concepts. If you have any doubts, please let me know so that I can repeat once again if you are not able to understand. Yes? Any doubt? If you have any doubts, please let. Have you understood the concept? What we are trying to do? Yes? What we are trying to do? We are trying to find out the extra attributes either in LHS or RHS. And we are having simple tests for that. How to determine that the attribute is extraneous in LHS? We need to check whether original set F logically implies new set F dash. What we need to do? If I want to check whether the attribute is extraneous in LHS, then simply what I need to do is I need to check whether original set F logically implies the new set F dash. And what is my new set? How I am going to find out this new set? I am testing for extra attribute in a particular functional dependency alpha to beta. So simply what I will do is I will omit the attribute under consideration from this functional dependency, right? And I may come up with this new set F dash. So if after omitting that attribute, if my original set can imply the new set, then I will say that this attribute is extra in my LHS. And for RHS, this test is simply the reverse test. So if I want to check whether the attribute is extra in RHS of the functional dependency alpha to beta, then what I'm going to do is I'm simply going to check whether the new set F dash can logically infer the original set F. And once again, how I'm going to compute this F dash? F dash is being computed in the same way. What I'm going to do is simply whichever is the attribute under consideration, simply I'm going to omit, I'm going to remove that attribute from the respective functional dependency from right hand side, and whatever remains is in my F dash, and I'll simply check whether F dash can determine original set F. If yes, then I'll declare that the attribute under consideration is extra. So we can omit that and we can come up with the simplified set of functional dependencies. Are you getting me?
Yes, ma'am.
Fine. So to practically test it, if an attribute is extra, we are having a simplified steps to test if any attribute is extra. So let us assume that we are having set of functional dependencies F, right? And let us consider one functional dependency in F of the form alpha to beta. Now, to test if attribute A that belongs to left hand side alpha is extraneous, we need to follow these two steps. What are these two steps? Step number 1, compute alpha minus A and closure of that using the dependencies in original set F. Right? What I'm going to do? I'm going to find out the attribute closure alpha minus A plus using the given set of functional dependencies F. And I'll be checking whether this closure that I have computed in step number 1 contains the right hand side of my dependency. If this closure contains the right hand side of the dependency, then I can declare that A is extra. You please take down these steps. We are going to solve the problem based on this. So please take down these steps in your notebook. To test if attribute A that belongs to left hand side of the functional dependency alpha to beta is extra, we are going to follow two steps. What are those two steps? Step number 1, compute alpha minus A closure using given set of functional dependencies F and check whether this closure contains the right hand side of the dependency. If yes, then we can declare that A is extra, meaning even though we remove that attribute from my left hand side, my left hand side can infer the right hand side of the functional dependency, right? And that is why there is no need to have this attribute A that is extra. So we can omit that. So these are the steps to be followed to test if attribute is extra in left hand side. Similarly, we are having the test for right hand side. So once again, take down these steps to test if attribute A is extra in right hand side of the functional dependency. What we are going to do is we are going to follow two steps. Step number 1, compute alpha plus using the dependencies in F dash. Right? So, what is alpha plus? It is closure of left hand side. So, I'll find out the attribute closure alpha plus using the new set of functional dependencies F dash. How to form this F dash? In the similar way that we followed earlier. How to find out this F dash? F dash is equal to F minus alpha beta union alpha determining beta minus A. Meaning, simply given F, you just omit the attribute under consideration from the respective functional dependency, and whatever remains is nothing but F dash. So compute alpha plus by making use of this F dash and check whether alpha plus contains attribute A which is under consideration. If it does, then we can declare that this attribute A is extraneous in right hand side of the functional dependency. So we need to follow these two steps. Right? So please take down these steps and we are going to solve one problem. Okay? So, let us solve now one problem. Testing if an attribute is extraneous given the set F. So, given the set F of functional dependencies as AB to CD, A to E and E to C. And we would like to check if C is extraneous in the dependency AB to CD. Right? So we need to check whether C is extra in the right hand side of the dependency AB to CD. Right? So here my alpha is AB and my beta, that is right hand side of the dependency, is CD. And we would like to check whether this C is extra in RHS. That we would like to test. Are you getting me? Yes? Are you getting me?
Yes. Yes, ma'am.
So, let us follow now the steps that we have listed earlier. So, what we are supposed to do? We want to check whether the attribute is extra in RHS. So, we need to compute alpha plus by making use of F dash. So, first of all, we need to compute this F dash. So, how we are going to compute this F dash? F dash is equal to F minus alpha to beta union alpha determining beta minus A. So, formally we are writing F dash like this. Right? So, what does this mean? F minus alpha to beta. So, alpha to beta means our dependency under consideration, AB to CD. Union alpha determines beta minus A. So, alpha is our AB, determines beta is our C minus the attribute under consideration. We are testing for C. So, CD minus attribute under consideration, that is C. So, give us F dash equal to F minus AB to CD. What does this mean? This is my F. So, simply I am removing this AB to CD from this F. So, I will come up with A to E, E to C, A to E, E to C, union AB to CD minus C. So, I am omitting this C from this right hand side, CD. So, I will be having D only. So, my F dash will include A to E, E to C, AB to D. Right? So, please see, this is my F and this is my F dash. So, formally, we are finding out F dash by following these steps. But it is in fact very much easy. So, what we can do is, see here, we are testing for this functional dependency and we are testing for this C. So, simply our F dash would be AB to D by omitting this C and the remaining dependencies A to E and E to C, A to E and E to C. Got it? So, this is my F dash. Are you getting me? Are you getting me?
Yes, ma'am.
So, have you understood how we found out this F dash? Yes? Have you understood how we found out F dash?
Yes, ma'am.
Is there any doubt? If you have any doubts, please let me know. So now, after computing this F dash, what what we are going to do is we are going to compute the attribute closure alpha plus by making use of this set f dash. Okay, so compute now attribute closure alpha plus. So here our alpha is AB. So we are going to compute AB plus, right? So we know the algorithm for computing attribute closure. So simply we are making use of that algorithm. So what my algorithm says, my result original would be AB. Then I'll pick this dependency. I'll check whether the left hand side of the dependency belongs to my result. So whether A is subset of AB, yes. If yes, then I'm going to concatenate the right hand side of the dependency with a result. So this is my new result. Okay, what next? I will be picking up next functional dependency E to C. I'll check whether E is subset of this. Yes. So what I will do is simply the right hand side is concatenated to all results. Okay. Now I'll be checking the next functional dependency AB to D. So once again AB is subset of my result. So the right hand side is concatenated. Right? So we are done with all these three dependencies now. Okay? And the result is AB ECD. So AB plus is AB ECD. Right? Now, what we need to check? We have computed this alpha plus. So what we need to check? We need to check whether alpha plus includes the attribute under consideration. So we are checking for C. We are checking whether C is extra. So whether this result includes this attribute under consideration C. Yes. So AB plus includes, and we may declare that C is extra. So we need not have this C in our set of functional dependencies. So we can omit this C and we may come up with the simplified set of dependencies. Is there any doubt? This is how actually we need to solve the examples. And we need to check whether the attribute is extra in either RHS or LHS. So right now we have seen the example wherein we tested the attribute in our right hand side of the dependency. Right? So I'm now giving you the exercise, homework. Right? So you test for whether this D is extra in right hand side, or you may test because we are not knowing which attribute is extra. Right? So we need to test for each and every attribute. If my functional dependency is having more than one attributes either in LHS or RHS, I need to test for every attribute whether it is extra. Right? So I am giving you the exercise now. You consider the same set of functional dependencies F. Right? And find out whether A is extra in this dependency, whether B is extra in this dependency AB to CD. We have tested for C. Okay? So similarly, you may test whether this D is extra in this functional dependency AB to CD. Right? So that you can have the practice of applying those tests. Got it? Yes?
Yes, ma'am.
Fine. So this is the homework for you. So next time you should come up with the solution. Okay. So we are just summarizing what we mean by a canonical cover now. A canonical cover for set of functional dependencies F is a set of dependencies Fc such that F logically implies all dependencies in Fc and Fc logically implies all dependencies in F and no functional dependency in Fc contains an extraneous attribute. Each left side of functional dependency in Fc is unique. Closures of F and Fc are same. Right? So if all these things are satisfied, then we say that we have come up with a canonical cover for F, which is a minimal set of functional dependencies. Those we can test. Right? So please take down this definition of canonical cover. A canonical cover for F is set of dependencies Fc such that F logically implies all dependencies in Fc and Fc logically implies all dependencies in F. No functional dependency in Fc contains an extraneous attribute and each left side of functional dependency Fc is unique and obviously closures of F and Fc are same. So if all this is true, then we say that Fc is the canonical cover for set of functional dependencies F. Right? In the next class, we are going to discuss a formal algorithm for canonical cover. Right? And we'll try to solve few problems for computation of canonical covers given set F. Right? I hope you must have understood. If not, please once again go through the contents. Right? So let's conclude the session today. Thank you.